Okay, hello everybody. Can you hear me? Thank you. So, today we would like to take in 1 hour to share you about the analysis of the separated excited DC motor. Okay, so in the lectures we talked about how to analyze the shunt, okay, and the series excited DC motors, okay, in terms of the loading, we said a torque, rotation, speed relationship. But today here, so we would like to talk about the general approach to analyze the performance of the DC motor with the separated excited motor as the examples, which is actually the approach we applied here is applicable to all DC motors. First, so we have a so-called equivalent circuit to represent the separate excited DC motor. So here, the left side is a typical field circuit that including DC voltage source to supply to major field coils. Generally we're using a so-called rheostat to control the field currents. Okay. On the other side, the right side is the motor's armature. We say the induction armature, including the loadings. Loadings. So RL here represents loading. Mechanical loading in electric circuit can also be represented by using a resistor. Okay, so resistor actually is the representatives of the loading. So from this circuit, we know that relationships for the field circuit, the field currents, the DC currents, is the effective field circuit voltage over the field circuit resistance. So here the resistance RF is the total effective resistance that used to control the field currents. Okay, so which including the field coil itself's resistance and the rheostat resistance, the effective one. Reading from the terminals of the voltage, So this is the voltage. From the two terminals, look into the systems. Look into the systems. There is a equivalent resistance. So that's the RF. Okay. So and also the applied voltage to the terminals. Field currents. Effective currents flow in the coils. On the other side, that internal generations, or we say here internal inductions. So internal inductions, the induced voltage cross the armature coils, and the proportional equal to so-called motor motional inductance factor. So K here is a inductive factor. Actually, so which more or less similar to the inductance issues. Or you can say to the reactance issues. So by here, so we just say it as the motional inductance issues. The motor rotation speed. This is the motor rotation speed and the DC field currents. So the product of these three factors determine the inductions. Induced voltage inductions. Here is the effective values. Mean square values, which for the DC motors is the DC output voltage. So on the terminals to the armatures, we have the input voltage. Here we're using the VA represented. So because this is the motors, so we have the input voltage that with the input loading currents or armature currents, RA here. So the RA is the total loading currents. Here is the input currents okay, from the source to the motor, okay, for inductions, for induced rotations. Here we by applying a current, therefore induce the voltage, therefore induce right torques and the rotations. So the applied voltage is bigger than the voltage induced on the internally on the armatures. Okay, so we explained it in the lectures already. So that's the three basic equations represent the circuit. Now, based on our needs, we can combine or change the above three equations to reflect one, the speed current relationship. The speed here so represents the motor speed. The current here represents the loading currents. Okay, so speed current relationship here. We do not show how we got this relation, but the combination above three. So in such a way, we found that rotor speed for a given terminal applied voltage VE decreases with the loading current IA. Of course, proportional, right? Inversely proportional to the KIF. So here, for more clearly, probably so. I should be right together. Okay. KIF, right, in the B divides the VA minus RA. And we also further to change, can change the above relations so that we can relate the torques with the loading currents. So the torque output torque, so induced torque loading currents relationship. Because here once again that the loading current represents loading levels actually. Okay. We may add more equations here. That is the power issues. Okay, so P, the rotations. So for speed, that is the internal powers. That's the E. A. Here is the R, right? Minus the I armature currents. And the internal induced torque on the rotor and the rotor speed, here we use the omega R represented. Okay, so in addition to these three equations, we write down one more equation here, although we mentioned this one in lectures, so that the on the armatures, we have the induced voltage ER, we have the armature current RA. So the products of ER and RA represent the electrical energies here. And it is these electrical energies that being converted into the mechanical energies in terms of the torque and the rotation speed. So these two is the air gap energies. Okay, they are equivalent. So torque times angular velocity is the induced voltage times the armature currents. That's the air gap energy. Okay, or converted energy here. So then we can find out the torque current relationships. So the torque proportional to the armature currents. Look at here. That's why we say that the loading currents or the armature impulse currents and the torques represent the loading levels. Okay. So now you're understanding the statements that we said in the mechanical, the torque, and in electrical, the current, okay, represent the loading levels. Okay, they are the same meanings. Okay, so because that the torque for a given motional inductance and field currents, which determine the induction, right? Determine the flux for inductions. So the torque and the armature currents, proportional to each other. Okay. And then we also can furthermore find out the torque speed relationships. So it shows that so the torques, when the field currents is given, motional inductance is given, applied voltage is given. Then the torques decreases with the increase of the rotation speed. Obviously here. So the rate of the decreasement, depends on the field currents. If the field current itself is very strong, then the decreasement of the torques with the increase of the rotation speed faster. That's the meaning of it. Okay. And also that's the powers, mechanical powers in terms of products of the torque and the speed in relation to the motor speed issues. So you look at the powers. Generally, if the speed increase for a given voltage, applied voltage, when the speed increase, so the powers at the beginning, when the speed be 0, the powers will be 0. As the speed increases, this formula is telling you that at the beginning, when the speed increases, the motor's powers increase. But at certain levels of the speed, the power will be reach the maximum. After that, if you further increase the speed, then the output powers will decreases. It decreases. Okay. So generally, so we cannot making the speed be very fast so that the motors has a big power. It is impossible. There are some balance between the speed and the powers. We must use motors in a suitable range of the speed so that the motor has enough powers to drive the object. But we just got some of the properties of the motor speed and speed currents and the torque currents, torque speed and power speed issues from the formulas given here. But this is not straightforward. We had been to given specific parameters, doing calculations and show them onto some diagrams so that we have direct feelings about how does their speed change with the torques, their speed change with the currents, or their torque change with speed, and so on. Okay, so now with these equations in mind and the general properties shown in mind, we're looking at the following examples for given a more parameters. Now, examples. Neglect the saturations and armature reactions for a 10 kilowatt separated excited motor with a motional inductance of K equal to 0.9 and the resistance of the field circuit 100 ohms and armature circuit 0.1 ohms. Draw the steady state performance characteristics Okay, and here neglect the saturation means that the supposed excitation is a linear one with a constant, okay, motional inductance, with a constant motional inductance. That's mu. And we have two cases. One, for a constant armature voltage, this is the input voltage in DC, VA 100 volts, and a field, voltage 100 volts, 75 volts, and 50 volts. So because this is a separate excited motor, so we have separate, field voltage and armature voltage. So here, for the served case, if we fix the armature voltage, okay, that is the source of the armature, and we change the field voltage to see, okay, for each case, how does, okay, the motor speed, the motor currents, the torques, and the powers changing. Okay, so the second case that for a constant field voltage, that means we fix the excitation strength at the field voltage 100 volts. However, we can change the armature voltage. So to see how does the motor performance change. The first case we can say is the first actually is the field voltage, control, field voltage control. The second case okay, so we can simply say, so that the case one actually showing you, so the field voltage control scheme for the motors. So in the motor in practice, we mean, by changing the field voltage to control the motor's performance, okay, of course, including the torque and the speed. The second case actually showing you, the control scheme of the motor with the variable armature voltage issues. So you will find that the performance of the motors under these two schemes are totally different. You have to based on the practical needs to take either the case one or the case two control schemes based on the practical needs. Now, go ahead and see too, for this given motors, for case one, if we fix the terminal voltage at 100 volts with the motional inductance given 0.9, whatever values here, and field circuit, resistance, equivalent resistance, 100 ohms, and armature resistance 0.1 ohms. Then, from above, equations, we bring in the given parameters. We can find out, one, the motor speed, loading current relationships. Because the VA is given, the RA is given, K is given, IF, of course, changing with the VF voltage. So here we bring in the VA 100 volts, and the RA 0.1 ohms. So we have the armature current IA, which changing with the speed Okay, and the chi given 0.9, and the field right currents, which determined by the VF over the RF. RF is given. Okay. Okay, so the field current RF equal to VF over RF. So VF is given, the VF is changing with times, changing, right? The RF is given. So then we have, okay, these right formulas. Here we have two variables. One is the, okay, armature currents. The other one is the field, okay, voltage. So the second one case is the second right formula is that the torque, okay, field loading currents, okay, and the field voltage equations. We also can bring in the given values, the K values, RF, which is related to the VF over the RF, so the armature currents, loading currents here, and also the output powers, okay, possible output powers torque, that powers motor, that is the product of torque and speed. So which, right, once again, so relate to the loading currents, right, loading currents relationships. Okay. Okay. Now, based on these three, okay, equations, we can get the drawings. One about the speed against the armature currents and different field voltage, 100 volts, 75 volts, 50 volts. First, we're looking at the speed. Okay, look at the speed, motor speed against the armature currents. So for the VA equal to 100 volts, and the motor speed decreases slightly with the increase of the armature currents. Okay, decrease slightly with the increase. So in a straight line, because here it is a linear excitation straight line. So when the field voltage becomes lower, say 75 volts, the motor speed higher than that when the field voltage be 100 volts. So if the field voltage be higher, the motor speed be lower. Okay. And also that the motor speed decreases with the increase of the armature currents, but the slope is a little bit bigger than that for the 100 volts. When the field voltage be 50 volts, half of the one, so you look that, okay, the speed of the motor will be almost double of the speed when the field voltage be 100 volts. So this gives you a hint that if you would like to make the motor speed be higher, then you can choose the field voltage be lower. So field voltage be lower, okay, getting a relative higher motor speed. Okay, motor speed. So this is the right when you want the motor speed to be relative higher, okay, you have to choosing the field voltage be relative smaller. Generally, it's a linear relationship between them. But pay attention to that. When the field voltage be smaller, that the fluctuations or the decreasements of the motor speed over the against the increase of the armature currents become bigger. Okay, because the slope be bigger. This slope be bigger than this one, but this speed be lower than this one. This is the speed against the armature currents. But when we're looking at the torques, so and when the armature currents be zero, of course the torque be zero. When the armature current increase, the torque increase linearly. But look at here. So for a higher field current, field voltage, higher field voltage, therefore the higher field currents, you can get a little bit larger torque increments. So in comparison with the previous figures, that for the speed, right, a lower voltage, field voltage, giving a higher speed, but the lower field voltage giving a smaller motor torques. Smaller torques. So if you would like to get the motor be stronger, that means get motor be powerful, be with big torques, you have to choosing a relative, right, bigger field voltage. So bigger field voltage giving more torque outputs, but the motor speed get down. So obviously, when the voltage be halved from 100 volts to 50 volts, the torque also be halved. Also be halved. So that's the characteristics. Now, also from the torque speed relationships, you look at the torque, generally speaking, when as the torque increase, the motor speed decreases. This is the first one. Second one, for a higher field voltage, the motor has a relative lower speed with bigger output torques. The increments of the torques with the decrease of speed faster. Faster. And for a lower field voltage, the motor speed are relative higher and the torque relative smaller, and the decreasements of the increasement of the torques with the decrease of the motors, decrease of speed, is not so fast. The slope of the straight line here is relatively smaller. This is the torque speed issues. Lastly is the power issues. So output powers and speed issues. So from these diagrams, and so I just explained to you, explained to you in previous page. At the beginning, when the motor speed be 0, of course there's no powers. When the speed increases, that the motor powers increases too. At certain levels, when the motor speed reach certain levels, then the converted powers reach its maximum. Then after that, when the motor speed increases, the powers decreases until be 0. Until be 0. For the three different field voltage, 100 volts, 75 volts, and 50 volts, the change rate of the power versus speed is different, as reflected by the curves here. The curves area is different, so the change rate is different. But their maximum power levels keeps no change. Maximum keep no change. So this because that the output powers, the output powers depending on the internal induced voltage times the armature currents. Armature currents. So if the field voltage is fixed, the field currents is fixed. So the powers just change with the armature voltage and the armature currents. So not affected by the motor speed. Not affected by motor speed. So the maximum so powers not affected by the motor speed. It just affected by the armature, by the armature voltage rather than the field voltage. So this is the case 1. So we have these statements. It is see that the speed falls by only a small fraction between the no-load and full load conditions, justifying the term constant speed characteristics. For this kind of motors, for the armature voltage be fixed and field voltage change it. So the speed changing, look at here. So go from here. Look at here. So for different torques, the torques change right from 0 up to almost 150 Newton meters. But the motor speed does not change so much. Okay, the motor speed, okay, from the beginning slightly higher than 100 radians per second, and when at the torques 150 newtons, it is about 100. Okay. So slightly higher than 100, okay, and down to about 100, about 100. So although the torques increased from 0 to almost 150 Newton meters. So this is the meanings of this statement. Okay. So for this kind of DC motors, okay, if we have a fixed voltage, fixed terminal voltage applied, okay, although the torque changed so much, but the motor speed keeps almost a constant. And also that powers for this case, okay, so the maximum powers of these motors be about 25 kilowatt and 1/2 of loading speed. Okay. Now we're looking at the second case, so which the field voltage be fixed at 100 volts, the armature applied voltage changing from 100 volts, 75 volts, and the 50 volts respectively. Okay. So the second case is the terminal voltage armature voltage control schemes. That means the field voltage be fixed, excitation strength be fixed, so field current be fixed. Okay. We change the terminal voltage, so that we control the motor's performance. So here the field voltage be given 100 volts, and motional resistance given, inductance given 0.9, coefficient. That's the field circuit resistance 100 ohms, and armature resistance given 0.1 ohms. So the motor speed, armature currents, and armature voltage relationships given here, and the motor torques, development torques in relation to the armature currents, because the field currents already be given. Field currents which given the VA over the RF. Okay. So also the powers that we as a functions of the armature currents and the terminal voltage. Look at the first diagrams we given here, which is drawn based on the above equations. So the horizontal is the armature currents RA, the vertical axis is the motor speed here. First, for a given field voltage 100 volts, with the terminal voltage 100 volts too. So motor, when the armature current be 0, that is the open circuit no load case. Okay, this is no load case. The speed is the highest one. The armature current is 0. Okay, no load. So the motor has a speed above 100 radians per second. As the armature current increases to about 150 amperes, the motor speed get down slightly. Get down slightly. So which is around 100 radians per second. However, when the armature voltage get down to 75 volts, Okay, then the motor speed under unload conditions get down by also about 25%. Okay, which is about 80, something like that. So as the armature current increases, as the loading level increases, the speed gets down, okay, linearly. The getting down speed a little bit higher than that for the 100 volts. Okay, so if the terminal voltage further get down to 50 volts, while that the armature, the field voltage, it keeps 100 volts. The no-load motor speed get down to about 50 radians per second, while that for the 100 volts about above 100 radians per second, half the weight. And also with the increase of the armature currents, the motor speed get down. Okay, the decreasing rates is a little bit higher than that for the 100 volts. But almost so similar slopes. A little bit almost similar slopes. No more difference between them. So this gives us a hint that so if you want to make the motors be faster, you can use a stronger armature voltage. If you want to make the motor has a lower speed, you can use a lower armature voltage. So lower armature voltage corresponding to a lower motor speed. Higher armature voltage corresponding to a higher motor speed. So this is frequently be used to control the speed, motor speed in practice. We just suppose the motor speed proportional to the terminal voltage, so linearly proportional to it. Okay, so this would be very easy, to understood. And a signal diagram showing there here. No matter, So what is the armature currents? So the motor torques, related to the armature currents, with a straight line that determined by that slope determined by the field voltage rather than the armature voltage. So with the same field voltage for different armature voltage, the slope of the torque increments with the armature currents, is given. So that means that it is the field currents that determine the torque increment slip with the increase of the currents, armature currents. In other words, it is the field current that determines how strong the motor torque is. Okay, now looking at the torque speed issues. Very similar to the above figures, it shows that for a higher terminal voltage, the motor has a higher speed. For lower terminal voltage, the motor has a lower speed. And when the motor speed increase, the motor torque development decreases. The decreasing rate for different terminal voltage, normal difference. Normal difference. So you look when the speed to certain values, the motor has zero torque outputs. That is the open circuit case. So the values on the horizontal axis corresponding to the zero torque represents the open circuit case, represent no load case. And this is the power issues. Different from the case 1. So the powers increase and beginning with the speed, then decreases with speed. At certain levels of the speed, that's the output power, the developed powers of the motor reaches like maximum. However, the levels of the maximum powers can be developed. Okay, strongly depends on the armature voltage applied. So it is armature voltage that determine the maximum powers of the motors. If the armature voltage be 0, the motor has 0 powers developed. Okay, so if you want to making the motors be powerful, you have better using a relative higher voltage, terminal voltage. So 100 terminal voltage, powerful. Okay, so on the other side, if you increase the terminal voltage, the powers increase. Meanwhile, the speed increase, right? So look at here, the speed also increase. The bigger speed also. Okay, so if you want to make in the motors has a higher speed with a powerful, with a big powers, you should making the terminal voltage be higher. If you want to make in the motors with big powers, but the speed be lower, but with a bigger torques, you have making the meanwhile you have making the field voltage be higher. A higher field voltage, so making the motors with a relative lower speed, but relative bigger torques. So in combination with these two cases, one can figure out, right? One, if you want to making the motors speed be higher, you can choose in either a higher terminal voltage or a lower field voltage. If you want to making the motors torques be relatively bigger, you should choose in that the field voltage be higher. If you want to making the motors has big powers, you should making the terminal voltage VA be higher. Okay, so if you want to making the motors has a big power, meanwhile has a slower speed but with bigger torques, you should guarantee that the field voltage, both the field voltage and the terminal voltage be higher. Higher terminal voltage guaranteed powerful. Big field voltage guaranteed the torques be bigger, speed be smaller. So we just have the two cases here, but in practice, you can based on the performance, based on the needs, right? You can choose and get different control schemes to achieve your purpose. That's the purpose of this tutorials. This tutorial tried showing you in practice how to using the control strategies to achieve your motor controls. So you can control the motor's torques, you can control the motor's speed, you can control the motor's powers by doing some combinations or some of the calibrations between the terminal voltage and the field voltage. Okay. So VA and the field voltage V8 can achieve various motor various motor speed, torque, and power control. Okay, so finally, I have a consumption, right? So here I have a summary about that. Okay, so in practice, so calibration between the armature voltage VE and the field voltage V8, we can achieve various motor speed, torque, and power control. But this is a summary about that. But specifically, how to control the speed, how to control torques, how to control the powers. Okay, so you should so understand that based on the looking at of these examples. Okay, so in your mind at least you should know that. Okay, and now basically speaking, if you want to the motors making the motor speed be higher, so you should making the terminal voltage be higher or the field voltage be smaller. However, when the field voltage be smaller, that's the torques be really smaller. When the armature voltage be higher, it is powerful. Okay, so you should understand these points. And also, generally speaking, that the motor speed, motor torques decreases with the increase of the motor speed. Okay. So, but in most of the case, that the change rate of the torque against the speed, is not so big. Not so big. Okay, so I think this is the end of the tutorial sessions for the DC motors. So although we just have two comprehensive examples shown in the tutorials, plus the two examples in the lectures, we have four straightforward examples showing you how to analyze performance of DC machines. So in practice, you can combine the different strategies to control the more DC machines, outputs. These machine outputs. Okay, so it is very useful, strategies in practice. Okay, so if you still have some any questions, you can write to me in the chat box or write to me via the emails after lectures. So anyway, so today is the last session, tutorial sessions, and after that, so in next week I will post the solutions for the two assignments onto the Blackboard for your revisions. Because the final examinations will take home examination, and also is an open book one. So I hope you can take the following 2 weeks, have a good revision on we learned in the lectures and the tutorial sessions. Okay, so that's the end of today's tutorial.